Now it started.
Yeah.
Okay. So what I'm going to be talking about first, we do some review of category with families, and actually not just a review, but we will finish it because there are some things which haven't yet been mentioned. So first we do this category with families, and this is basically just some kind of the theory of doing substitutions on terms and types. But this doesn't really have any interesting types. There are no types. If we are only talking about the category with families, we only know how to do kind of a generic theory of substitution. How can we get De Bruijn indices and so on. And if we can finish that, we will talk about some interesting type formers such as functions and pair types and universes and maybe identity types. And I'm not sure we will finish this, but if we finish it, then we can start talking about the standard model of this type theory. So up to this point, we are not talking about any particular model of this type theory. We are just talking about what is a model of this type theory. So all of these components are just the components of the notion of model of type theory. Okay, so let's start with CWF. So we have 4 sets in a CWF. We have con, which is set of typing contexts, and the typing context can be understood as a list of types. And we also have types, which is a family of sets indexed by context. So these are types in specific contexts. And the reason that we need this indexing on context is because we have dependent types. So it is possible to write down a type such that it refers to a variable in the context. For example, like what is a type in the context? We've previously seen these vectors, so I can have something like a vector with length n naught, where n is a variable. Maybe let's write bool here because it's perhaps a bit less confusing, because here we have this n, which is a natural number, but it only indicates the length of the vector, and this bool should be the type of the elements of the vector. And this is an example of a type which depends on a number. So this is a dependent type, and it can depend on a variable. Okay, and we also have terms. So terms live in some gamma context and have some type. So terms in gamma context with a type in that context. So this is a family of sets which is indexed over contexts and also indexed over types. And this notation for this function type is it's a dependent function type, but it's a dependent function type which lives in the meta theory. So we can define such functions in set theory, but we can also define them in type theory. So this is just a dependent function in the meta theory or in mathematics. And we also have substitutions, which is con set. And this is a parallel substitution. And so one way of thinking about the parallel substitution is that whenever we have a sub from gamma to delta, then this is basically assigns a term in gamma to each variable from delta. So, so this can be viewed as a list of terms. List of terms such that we have one entry for each entry in delta. So one list entry for each entry in delta. Okay, but we are going to see a lot more examples for substitutions. So I mentioned before that the typing context is a list of types. So let's just define the empty list of types and the extended list of types, and that's going to be the only way that we can use to form contexts. So there is an empty context, which is just this. And we also have an operation to extend the context with a type. And we are extending a context on the right, so this can be viewed as a SNOC operation. So this is kind of a linked list of types, but the extension happens on the right of the list. So whenever we have a context and a type in that context, we can create a new context. And this notation is kind of an Agda notation, so you can use this comma operator in an infix way. So if we have gamma and a, then we can do gamma a. Okay, and this is pretty simple. So context. And what about substitutions? I mentioned that substitutions can be viewed as lists of terms. So let's also try to define the operations for creating an empty list of terms and also an extended list of terms. So there is this epsilon, and this is a substitution from gamma to empty. And another note is that whenever I am writing down a gamma like this here, it's basically implicitly universally quantified. So it's kind of, so gamma is an implicit argument to epsilon. And so we were using this implicit argument in the previous type theory, meta theory session, and we are going to use them here as well because it's very helpful for readability. But you need a space after gamma, asks Donko István. No. In Agda, we would need a space, but in informal notation, we don't need a space. In informal notation, it's often very helpful if we don't have to put spaces everywhere. And I think it would be an improvement in Agda if Agda could also do some operators without mandatory spaces. But this is kind of off topic. Okay, so okay, so you have the empty substitution, and this says that for any gamma, we have a substitution into the empty context. And I mentioned previously that this is a list of terms such that there is one entry for every entry in delta. And in this case, there are no entries in delta because delta is empty. So if delta is empty, then the substitution is an empty list. And likewise, when we have an extended substitution, then the extended substitution is going to return in a non-empty context. Let's just write it out. So if we have a sigma, and this is So let's also summarize the notation for variables. So for context, we are usually using uppercase Greek letters. We can pick some uppercase Greek letters. For substitutions, we are using lowercase Greek letters like this. So if we have a substitution from gamma to delta, and we have a term in gamma with type A of sigma, but I will also write out the type of A in a moment. Then we have a substitution from gamma to delta extended with A. And let's write out the type of A as well. And we can also use Agda notation here. So gamma and delta are quantified implicitly, but let's introduce A explicitly. So A is a type in delta. And you can see that this makes sense if A is a type in delta, because here I'm writing down an expression where I'm extending delta with A. So A must be in delta. But I mentioned that the substitution is a list of terms, and every term in the substitution has to be in gamma. So I can only extend this list with a term which lives in gamma. So I have to use a substitution of types here to bring A into gamma. But so let's also introduce the type substitution, which was mentioned last time as well. So there is an operation which substitutes types. So if we have a type in delta and there is a substitution from gamma to delta, then there is a type in gamma. Okay. And I think we should give some concrete examples for doing type substitution. We can use this vector example. So for example, a vec of n of bool, and here, so this is informal. So here in this example, I am still using the names for variables, but of course, formally we are only using De Bruijn indices, but we haven't yet introduced De Bruijn indices. So just for the sake of the example, I'm using names here. And likewise, we can have an informal notation for context as well. So instead of gamma A, we can write something like gamma extended with an X in A. So in informal notation, it is very helpful to use names. So vec and bool is a type in a context which looks like, for example, this. This. And what kind of substitution can we use to bring this vec and bool into some different context? So for example, so in this case, we have the delta. So vec and bool is a type in delta, and we have delta equals the empty context extended with an actual number. Let's also define some gamma. So let's define gamma as the empty context. Let's just have gamma as the empty context, because this is a very simple example if you do it this way. So in this case, let's define sigma, which is a substitution from the empty context to this context, to be Okay, so find this substitution. So the substitution goes into a typing context which has length 1. So this is also a list which has length 1. So we start with epsilon and then we extend it on the right with a single term, and I can write down like a suc0. Now, so this is a type which depends on a variable. However, if you are doing a parallel substitution like this, and this is a type in the empty context. And actually, we can compute the substitution. So the substitution is not really a static thing. It can be viewed as an operation. So substitution performs some computation on all type formers and also on all term formers. So it basically, substitution goes inside all of the subterms in terms and types. And for each variable, it performs the appropriate like lookup or De Bruijn index shifting operation. And in this case, this is going to be just equal to rec of suc0 of bool. And maybe you are familiar with the notation for parallel substitutions, which is also kind of an informal, but you can find it in textbooks or papers. And in this case, I can write it as a substitution which maps n variable to something. I think most people are familiar with this notation. Is there someone who haven't seen this before? No. Okay. Okay, so let's continue with substitution. So we have the empty substitution and we have the extended substitution, but we also have some rules for like uniqueness of substitution. What do we mean by uniqueness? So first, we have a rule which says that every substitution which goes into the empty context must be an empty substitution. So first, like this is the uniqueness of epsilon. Let's call this epsilon eta. So in type theory, if there are uniqueness rules, we usually call them an eta rule. So this is kind of a suggestive notation.
Sorry. So just so that I understand the example correctly, so it is a type in the empty context because there is no longer a dependency, because
yes.
suc0 is well defined.
Yeah. Yes. So suc0 is just a number, so it doesn't depend on any variable. And so if we perform the substitution on vec and bool, then the result doesn't depend on any variable. That's why it is a type in the empty context. Okay. So we have this uniqueness rule, and this uniqueness rule says that if we have any substitution which goes into the empty context, then that substitution must be empty. So for any substitution like this, that substitution has to be equal to epsilon. So every sub into must be empty. So this is the uniqueness of epsilon. And And we cannot yet talk about the uniqueness of non-empty substitutions, but we will be able to talk about that shortly. Okay, but at this point we know that substitutions are parallel substitutions, and they are kind of lists of terms, and contexts are lists of types, and we have an operation on types, which is the substitution. But before we go forward, so let's make this picture a bit more complete. So there are some equations. Okay, sorry. So first, okay, so first, let's mention some particular substitutions which are important. So there are the identity substitution. And the identity substitution can be understood as a parallel substitution which maps every variable to itself. So kind of maps every variable to itself. So informally, if you have an identity substitution, which, for example, goes from x in bool, y in bool, to the exact same context, then so if you have an identity substitution, then an informal notation for this substitution could be like we are mapping x to x and y to y. And if you have a substitution which maps every variable to itself, then basically substituting with the identity substitution does nothing. So we have ID, which is a substitution from gamma to gamma for any arbitrary gamma. So we have this ID, and we also add the rule that substitution, the type substitution with ID does nothing. So we have the rule, which we sometimes call this. So this is the name of the equation, and the equation says that for any type, and let's introduce this. So for any type in gamma, an A substituted with ID is equal to A. So we have this identity substitution, and we also have a composition substitution. And we call it like this. So if we have a substitution from delta to sigma, and we also have a substitution from gamma to delta, then we have a substitution from gamma to sigma. And what's the intuition for a composition of a substitution? So if I have something like sigma delta, then we already know that the substitution can be viewed as a list of terms. So here, sigma is a list of terms, and this composition operation also computes. So like substitution computes on every type former and term former, and likewise this substitution composition also computes on particular substitutions. So the way this works is that sigma is a list of terms, and this is basically applying the operation which is a term substitution with delta on every term in sigma. But we haven't haven't yet seen term substitution, but term substitution is very analogous to type substitution. So this is kind of a preview. And so you can interpret this composition of substitutions as performing a substitution on every entry in a list of terms. And we can work out that actually this is going to have this type, but that will be maybe more apparent a bit later. Okay, so we have this composition, and we also want some equations. So we want associativity. So we have that sigma delta happening here. Oh, okay. So we want this composition to be associative. And we also want composition to be unital with respect to identity substitution. So we have this left identity rule, which says that if we compose ID with anything, then we get back anything. And we also have the right identity rule, which goes as we expect. Okay, and for example, so if we are using the previous intuition, so does this hold kind of informally if we are just appealing to this kind of list intuition for substitution? So here, ID is just a list of variables. So here ID is a list of variables, and every variable is mapped to itself, and we want to perform the sigma substitution on every variable. But if we are performing a substitution on a variable, then it's just going to look up. So it's just going to look up the term, the corresponding term from sigma. So sigma is a list of terms, and ID is a list of variables. And performing this composition just looks up a term from a list of terms. So what is going to happen is that we just get back exactly the same list of terms that we started with, which is sigma. So what happens here? So here sigma is a list of terms, and we want to perform the identity substitution on every term, but the identity substitution does nothing. So again, if we perform nothing on every term in sigma, then nothing happens, so we still get sigma. So this is kind of an intuition for why these rules should be true. But here we are just saying that these rules should be true in any model. So these rules will be true in the syntax, but these rules will also be true in any model of type theory. Okay, and we also want to say something about it.
Sorry, we could also say that the composition of two substitutions is basically like first substituting the variables in sigma with the terms. I mean capital sigma, the context, with the terms in lowercase sigma, which is a list of terms, and then substituting those the variables in capital delta with the terms in lowercase delta, right?
I'm sorry, but I was not able to follow.
Sorry, so I wanted to say that substituting can also be viewed as a first composition can also be viewed as a first substituting the variables with the terms in sigma, then substituting the variables in the terms in sigma with the terms in delta.
Yes, I mean,
right?
Yeah, so there are a lot of ways of factorizing these operations, and but yeah, so there are a lot of ways of performing the same substitution operation, but you can specify it differently. So that's why we have all these equations, so that all of the different ways, all the superficially different ways, can be identified. So that's true that we can think about it that way as well. And here in my informal examples, so I am trying to appeal to just a very specific way of computing substitutions, but which is kind of canonical. So I'm trying to appeal to a specific way of using substitutions as lists and substituting a variable as lookup. So I am kind of appealing to lookup from lists, which is, I think, a good way to think about substitutions, because that's how the real-world implementations of functional languages also work. So in the real-world implementation of a type checker or a functional language, what happens is that we have some environment of values which looks like a list of terms, and then when we have a variable, we look up the corresponding value from the environment. So I think that's a good way to view it.
Okay, I see.
But there are many different ways to kind of compute substitutions. But I think this is a good way to just mentally try to visualize it. Okay, and we also want to say something about the interaction of type substitution and composition and identity. So we want to have a rule which says, okay, we already have this rule. So we have this rule which tells us about the action of identity substitution on a type. And we also have a rule which is about the action of composite substitution on a type. So if I have a type and I substitute a type with a composite substitution, then it's the same as performing two substitutions one after another. And here in this notation, we have parents like this. So we have a sigma, and then we are doing substitution with data. Okay. And I think now we can return to this thing. So we have a uniqueness of the empty substitution, but we also want to talk about the uniqueness of the non-empty substitution. For that, we specify one substitution, which is called P, and P is a substitution from gamma A to gamma. And I'm not sure what's the story behind the naming of this, but this is, I think, wants to be a first projection substitution. And the way P works informally is that we basically, so we have a list for every entry in gamma. Okay, I'm not sure what's a good way of thinking about this. Maybe the best way to think about this is that this is kind of, you can use P. So basically, we can use P to bring any type or term in. So if we have a type or term which is in gamma to gamma A. And this is called the weakening rule in logic and also in type systems. which says that if you can define anything which lives in some gamma context, then you can also bring the same construction to any context which is larger. So anything which depends on gamma can be defined in any larger context. And in this case, we can only use P to weaken things in gamma to gamma extended with A, but of course we can also use P several times, so we can use P repeatedly to also bring things from gamma to some larger delta. Okay, so we have this P. Okay, I think let's also just write down first. I'm sorry, I'm doing this in a bit random order, but let's also write down term substitution. So if we want to do term substitution, then we have a substitution from gamma to delta, and then we have a term which is gamma and has type. So we have a term which is in delta and has type A, and then we get the term which is in gamma and has type A sigma. So the type substitution brings a type which depends on delta. So if there is a type which depends on delta, then we can get a type which depends on gamma. So there is kind of a flipping there, and there is a flipping here as well. So if there is a term which depends on delta, then we can get a term which depends on gamma. However, we also have to perform the substitution on the type, because otherwise this would be nonsensical, because here we are mentioning A as a type in delta, but here we have to mention a type which is in gamma, so we have to use type substitution.
Aren't the parameters flipped in substitution?
So the action of substitution is kind of flipped, because if you have a substitution which goes from gamma.
I mean first the terms and then the substitution in the operation.
Sorry?
Like aren't the parameters to this operation flipped? So first the term and then the substitution.
Oh yeah. Right. Okay. Sometimes I am writing it in the other way, but this is more common to write it this way. But I always mix them up. Yeah. So you're right. This is term substitution, and okay. And now we have this first projection substitution, and we can also see why this is called first projection. And the reason it's called first projection is because we can use P to take kind of the first component of an extended substitution. So and there is actually a computation rule which expresses exactly this. So there is this rule which we can call P composition, and it says that if we compose P with sigma T, so sigma T here is some substitution which goes from some gamma to delta extended with A. So we know that it goes into an extended context because it is an extended substitution. So this goes from gamma to delta A, and P here goes from delta A to delta. So if we are performing a first projection after, so the substitution can be kind of read from right to left, the same way as the function composition can be read right to left. So with the plain functions, we have like f composed with g is lambda x dot f gx. So the function composition, so the action happens from right to left, because first we are performing g and then we are performing f. And the substitution composition is a bit similar, because we think that the action of the substitution first happens on the right and then it happens on the left in a composition. So this is a substitution which does this extend bit substitution, but then does a p, and the rule says that this is just sigma. Nicely, I think this is probably the best way of viewing it. So the best way of viewing p is that p composed with sigma p is just sigma. So this p composition operation can be used to project the first component, to take the first component of a list of terms. So if you are thinking about SNOC lists, then it's kind of an init operation, SNOC list. Yeah. So we have a substitution which can be used to take the initial component of an extended substitution. And we also have something which can be used to take the last component of an extended substitution. And that's called Q. And this is kind of a second projection. But if you remember, when we are doing an extension of a substitution, so here is the rule for doing an extension of a substitution, then we are only snocking a term. So the second projection has to project a term from a substitution. So if we have some sigma, which is a substitution which goes from gamma to an extended delta, then we can get back what's kind of stored inside sigma. So we can get a term in gamma, but now we cannot write a here. So a would be wrong because a lives in delta, but here we want to get some type which lives in gamma. So what we can do is that we substitute a with sigma. So then a sigma is a type so a is a type in delta, and then a sigma is not correct. So how should this be? I think this should be P sigma. Yeah, okay. I'm remembering it. So A is a type which is in delta. So AP is a type which is in delta A. But we want something in gamma. So we are doing AP and then sigma. And sigma is a substitution from gamma to delta A, so we are fine. So this is a type in gamma. But usually, so this is just a convention, but we usually kind of contract these iterative substitutions using the previous rule. So we can instead just write P P sigma. Okay, so this is the second projection. And then we have this computation rule, which says that this is indeed the second projection from a list of terms. So if we are, but now this is not a composition anymore because Q is a term, and there is no operation which does composition on terms. There is only a substitution operation on terms. So this will be a substitution rule for Q, which says that if we substitute Q with sigma T, then that's equal to T. And now we can actually start CDR. CDR is like a first projection operation in Lisp. No, second projection operation in Lisp. Yeah. So Q can be viewed as, so we can have a car CDR, and P is car, and then Q is CDR. Now we can actually talk about De Bruijn indices.
Sorry, before we start that, I tried figuring line 72 out, but I still haven't managed to. I'm still stuck at the point where I think that the composition is swapped. Can we write out the types of A, sigma, and gamma?
Okay.
Delta, sorry.
Okay. So what we have here is we have A is a type. Okay, so let's write it out. So sigma goes from delta to sigma, and delta goes from gamma to delta, which is the same way what would happen with functions. So if we have function composition, then there is something which goes from B to C, and then it's something which goes from A to B, and then we get something which goes from A to C. So if we have this, then the composite goes from gamma to sigma. And if A is in sigma, then A sigma is in delta. Is that correct? Yes?
Yes.
And A sigma delta is in gamma. And likewise, A of sigma delta is also in gamma.
Okay, thank you.
Okay, so I think all of this requires practice. So this is basically, so what we are defining here is kind of a very precise formalism for performing substitution. And if you think about substitution, so there is a lot of intricacy about substitution because we have all these De Bruijn indices, we have level shifting, we have this weakening substitution. Actually, the weakening substitution corresponds to level shifting. Yeah, Vispi?
So what I'm thinking, I'm thinking perhaps we could make a drawing somehow of this because I am having flashbacks to 40 and solving solutions through row, but all these lines are getting a bit convoluted without, I don't know, some sort of a drawing which set is where and how, and I don't know, maybe it would help.
Okay, I think what we could do is that, so this part is almost over now. And so this CWF, which is kind of this theory of substitutions, it's almost over. And I finished the definitions, and then we look at lots of examples just using all of these components.
Okay. So just one more question. So CWF is like the mathematical bedrock kind of thing, or
yeah.
So
all of these equations and components which I'm writing down,
and the rules,
sorry,
and the theorems. So like these definition like rules such that, yes.
So these rules are more like axioms. So if you think about some structure, like for example a group, then a group has some equations inside the definition, and it also has, like, a group has a set of elements, and it also has some binary operation, and then you have some equations on the binary operation,
which it must satisfy, right?
Which it must satisfy. And now I'm defining an algebraic structure which is called category with families, and it is a lot more complicated than a group, but it also has some sets and families of sets. And whenever I'm writing like this, it's an operation, and whenever I write something like this, it's an equation.
Aha. Okay, thank you.
So are sets in the meta theory of CWF, that is mathematics of some kind, or?
So whenever I'm writing set here, it's just a set from mathematics, from the meta theory. And also whenever I'm writing a function arrow like this, it's also a meta theoretical function space. And whenever I'm writing an equation, like an equality like this is the notion of equality in the meta theory. So the same way that we use sets and equalities to define groups, here we are using sets and functions and equalities to define CWF. Okay. Another hand is up. István.
Sorry, it just remained there after struggling with 172.
Okay. So now we have P and Q. So we can do these projections from substitutions using P and Q. But an important thing is that we can use P and Q. But another question, can't one also use these function spaces as derivation rules? At this point, not really, because so if we want to talk about the syntax, then yes. So if we talk about the syntax, then we can use every operation as a derivation rule. So we can view every operation as a derivation rule if we want to talk about syntax of type theory. But we are not necessarily talking about the syntax. We can talk about an arbitrary model or algebra of CWF, the same way that we can talk about an arbitrary group. So for groups, there is a specification what a group is, which is all of these components and equations, and there are particular groups, and the particular groups are models of the group signature. And here we have this specification of what a CWF is, and a particular CWF is basically some structure, or basically it's a big record such that everything is defined. So we have a con, a tie, a tm, a sub, and all of the operations have some particular definitions, and all of the equations have proofs. So all of the equations hold for the particular definitions. And if we are talking about the initial model, then it's the syntax, and then an operation is really like a derivation rule. But we can talk about other models which are not the syntax, and then the operations are not really like derivation rules, or not necessarily like derivation rules. Okay, so now De Broglie indices are everyone's favorite. So we can use P and Q to define De Broglie indices. So how does this work? The way it works is that if you remember, so okay, here I made a mistake. Okay, so I think this is wrong because this is actually just TM. Now, so I mixed up another definition of P and Q. So there are like slight variations of definitions of P and Q, but they are all equivalent. And here I did a mix-up because I started to write down a definition of Q, which is in the other style. So sorry for that, but let's review this other definition. So Q is just a term. So if we have an implicit argument type, which is in gamma P. Okay, actually this is not like this. So this is like this. So we have a term which lives in an extended context and has this type. I'm very sorry. So A is a type in gamma. So if we do an AP, then it's a type in gamma A. So that's why this expression here is well typed. And then if you think about it, now this equation makes sense because sigma T is a substitution which goes from gamma to delta extended, and sigma is a substitution just from gamma to delta, and T is a term with type A sigma. So if we are doing a Q substitution with sigma T, okay, let's first just type Q. So Q is a term in okay, I have to think about it a bit. Well, what is the type of Q here, Ambrus? Ambrus is very good at immediately figuring out the type of Q. Maybe Ambrus is not here. So sigma T, it goes from gamma to delta A. So Q is something which goes from delta A to AP, right? Okay, I can do it as well. So this is not easy, but actually this is exactly as hard as the handling of substitution is in any implementation of programming languages, which is also quite hard. And this is basically just a very precise formalization of all the difficulties which can arise with substitution and shifting indices and whatever. I think it's very helpful. So if you learn how to do these typings in your head and how to calculate the substitutions, then in my experience, it's very, very helpful if you actually do some compiler implementations. And then you do complicated manipulations of scope and inserting things to scopes and shifting variables. It's very helpful because you get some good kind of a formal intuition for doing substitutions. Okay, so Q is a term in delta A, and if you substitute it, then it becomes a term in gamma with type. And now this is already kind of interesting because originally the type was AP, but now because we are performing a substitution on a term which has type AP, we are performing another substitution with the substitution So this has type this, but this also has type this, because we have the rule which says that iterated type substitution is just a single type substitution with a composite. So then this becomes this. We have a computation rule for P composition, and the computation rule for P composition says that this is just this. So we see this equation, and on the left-hand side, we have a term with this type. And on the right-hand side, we also have a term with this type. And this is already kind of non-trivial, because the reason this rule is even well-typed is because we are appealing to some equations which we introduced previously. So here we are appealing to this equation, and here we are appealing to the P composition equation. And this comes up in many places. So basically, when we are doing reasoning about dependently typed substitution, everything is well typed up to all the rules of substitution. And if you ever see something, so if you are trying to do some equational reasoning, like on paper, as we are doing now, and if we encounter some term which is not well typed, like we are doing like an equational reasoning or a simplification of types like this, and if we arrive at something which is not actually well typed, then we know that something went completely wrong. And sorry about this. So now we have this Q, and now we can talk about de Bruijn indices. Okay, so what are de Bruijn indices? So de Bruijn indices basically are pointers into the context. And de Bruijn indices are basically counting kind of from the right. So they are counting from the right of the scope, from the right end of the scope. So informal examples for defining something with de Bruijn indices. So if I want to define like a lambda x dot x, then I can define it as lambda 0. And if I want to define lambda xy dot x, then with de Bruijn indices, it looks like we have two lambdas, and then we would use one. Or maybe let's write both of these lambdas here, because it's maybe a bit clearer, and let's also write it both. This 0 points to the rightmost thing in the scope, which is like it's the nearest binder. So it points to the nearest binder. And this one points to the binder which is after the nearest binder. So this x points here. So it has to jump over one lambda, and that's why it's not 0, but it's 1. And we can use P and Q to reproduce this. So I say that the index 0 is just defined as Q. So maybe V0 can be defined.
What do you mean? Sorry, what do you mean by P and Q? Did I hear it properly?
P and Q. So
P and Q. Okay.
And
So
Q.
the
So what
previous
I'm
two
saying is that we can define all de Bruijn indices using P and Q, and that's what I'm doing now. So I say that the 0 index, so the de Bruijn index which corresponds to 0, or maybe Balázs suggested that it maybe works in Agda to write like this. this okay? It looks a bit funny.
The font is a bit too small.
I can make it larger, or I can use just V1 and V0 instead. Balázs says that there are some variations with the right arrow. So let's try it. Maybe. One would prefer the special characters. Okay, then no. Okay, type 1 and press the right arrow at the end. Okay. Okay. So there is. What about this? This is also a bit small, but maybe more legible.
Yeah, I think this is okay. Just make it a bit bigger.
But now I think the problem is that with 0 I don't have a choice. Agda doesn't give me any choice for 0. It only gives me a choice for 1. So let's just make the font larger. And then also use just for consistency. Let's also use. Maybe the second variant for 1 as well. 2. Oh, it's a bit of a mess. I mean, it's. Now it's consistent. Is this okay?
Yes.
Okay, so the tuple index 0 is just defined as Q. And then what is the type of Q? So it's a term in an extended context with this type. So, but this is just what the 0 de Bruijn index is. So it's a variable which points to the rightmost context entry. And we can see that if we extend gamma with A, then we have a variable which points to the rightmost context entry. So that's why it has type A, but of course it cannot exactly have type A because A lives in gamma, and now we need to have something in extended gamma. So that's why we have to use P to bring A into a larger context. Okay, and what about the index 1? So first let's just try to type the index 1. So I claim that what we want to have is that in any context which is extended twice, so we want to have a variable which points to A. So we want to skip over B and we just want to point to A. So we want to have something which type, but now A lives in gamma, and now we want to have something in gamma, comma A, comma B. So we have to use P twice. How can we define this? So we already have some Q, and as a first step, we can use Q to get a TM just from gamma A to A, right? But this isn't really what we want because we want to skip over this B. But we can use a substitution of Q with the P to just do that. So we have a Q, which is the de Bruijn index which lives in gamma A and points to A. So we already have that. But we can use substitution with P to skip over an additional entry in the context. So then we have a gamma A, B, and then we have A, and because here we are doing a term substitution, we also have to do a type substitution, so this becomes PP, and this is the definition. And I just put this here as a comment. And sometimes we are using a notation like the iteration of P. So this is a notation for iterated P, and we can use something like P square. And P square is the same as P. And as a special case, I mean, not really a special case, but it can also happen that we have P0, and then a P0 is just the identity substitution. This is just a notation. So the P is called weakening, and the P squared is basically it weakening twice. Okay. So in general, what is the definition? So in general, De Bruijn index, which we can call maybe this I, but now I cannot get the special font, but this is general De Bruijn index. So general De Bruijn index is defined to be P substituted, Q substituted with P to the power of I. So why is that? The reason is that if we have Q, P0, that's just Q of IB, which is just Q, which is the zero De Bruijn index by definition. And otherwise, if we have some QP of I, that's basically skipping over I entries in the context. Okay, so this is the fully formal definition of De Bruijn indices. And now that we have this, Dolko István says that if I write this, okay, can we make it even better? Yes. Thank you. Now it's perfect. So we have De Bruijn indices, and now this is the kind of the last part of the CWF. So we are almost finished with CWF. We only have to talk about the uniqueness of non-empty substitutions. So uniqueness of sub gamma delta A. And how can we talk about this? So maybe let's call it comma eta. So this says that if we have a P comma Q, that's the same as IB. Let's write some types here. So here P goes from gamma A to gamma, and Q is a term in gamma A with type AP. And if we are combining them, so if we are snocking them together, then it says type sub gamma A and gamma A, right? Because TM has type if substituted with P, but here we are using P as the first component of an extended substitution. So this is well type. So the left side of the equation is well type, and the right side of the equation, of course, it can be well type because ID can have type gamma A, gamma A. So from this we see that the types are okay in the two sides of the equation. And now I'm saying that a P extended with a Q should be the identity substitution. And what's the intuition? Intuition. So I think the intuition is that that now we can maybe view P as a substitution which P assigns every variable to the same variable, but in an extended context. And actually, this is called shifting de Bruijn indices. So whenever we are doing a substitution with P, so TP has the result of shifting all indices in P by 1, and of course up. So adding 1 to every de Bruijn index in P. And if you think about it, so P is a substitution which goes from gamma A to gamma. So if you have a term which is only in gamma, then if you want to bring that term into an extended context, then we have to increment all the de Bruijn indices inside the term to make it type correct. So this is another intuition for P, and for Q. So Q is just the 0 index. So if I am combining P and Q, then this is it's basically this becomes the substitution which assigns every variable in gamma to the same variable, but in an extended context, and we are also assigning the 0 index to itself. So what happens is that in the end, we are just assign every variable in gamma A to the same variable in gamma A, which is the identity substitution. Or maybe another way of thinking. Okay, let's not talk about that. So maybe for now this is enough. And okay, so we have this uniqueness rule, and actually I wasn't completely correct because we also have a rule which we just skipped for some reason. Let's just go back and add the rule. So when we had the substitution extension, where is the substitution extension? So here we have the substitution extension. We also have the rule which says like what happens if we are doing a composition with an extended substitution. So we have this rule which says that if we have sigma t and if we compose it with delta, then that's just equal to sigma delta and t substitution. So this is kind of the rule that says that the composition, so the substitution composition basically performs substitution for every term inside the substitution. Basically, sigma delta performs the delta substitution for every term in sigma. Okay, so because here we have an extended substitution like a list, and there is a term. So for the term, we perform the substitution, and then we recursively do this composition for the initial part of the substitution. And there is also a rule which says like what happens if we want to compose epsilon with something. So what happens if I want to do a composition on the empty substitution? Anyone has any idea? But this is
it
actually
should be sigma.
No.
But
So here I'm saying that if I'm doing substitution composition, then on the left side I have a list, and I am mapping over a list with substitution of data. So if I am mapping over an empty list, then what happens?
it stays empty.
Well, you get an empty list.
Yeah, it stays empty. But actually, I don't have to add this rule. Why?
Yeah, because the type prescribes that it will be a substitution from the empty context.
Two, yeah.
Sorry, yeah.
So epsilon composed with anything has type into the empty context, and there is a rule which says that that everything which has this type is equal to epsilon. So this rule specializes to saying that epsilon composed with anything is epsilon. So we already have the uniqueness rule for epsilon, and we can just use it. So this is we don't have to add this rule because this is derivable from other rules. And with this we are finished. So this is we are finished with CWF, and now we can have some examples, and and I think for examples we can also do some other like rules which can be derived from other rules. So here we see one example for a sensible looking rule which can be, so we have the sensible rule which can be derived from some other rules, but we can also have some other derivable rules, and we can also have some other derivable operations. For example, and we usually use this derived rule quite often. So uniqueness of non-empty substitution. So we had this rule, but this rule is kind of abstract. So usually we want to have some uniqueness for some arbitrary sigma, which goes from gamma to delta A. So what is the uniqueness rule for a concrete sigma substitution? The uniqueness rule should say that sigma is actually non-empty. So I say that every substitution which has a non-empty target context should be non-empty. So every such sigma should be equal to an extended substitution. And the rule or the equation says that every such sigma is equal to sigma p extended with Q. Am I doing right? So every sigma should be p sigma, right? And Q sigma. So every such sigma is actually an extended. And can we prove this from the previous equations? Okay, probably this is still a bit complicated for a basic example, so I just do it. So yes, this is provable because if you think about it, so we have an extended substitution such that the initial part is composed with sigma, and the last part, like the term part of the substitution, is also substituted with sigma. So we have a rule for this, which is the mapping rule, kind of the mapping rule. So we can just factor the sigma out. So we have a PQ and then sigma. And here we are doing equational reasoning, but not in the direction of like what we would use for computation, but in the reverse direction. So we have a rule which says that this computes to this, but we can also use as equational reasoning in the other direction. So we factor out sigma. But now we have a rule that PQ is just the identity substitution. So this is the uniqueness rule. So this is ID sigma. And we also have a rule that the ID does nothing. So it disappears and we get sigma. So this is for a derivable equation. Now there is a homework, and the homework is not very easy, but it's also not super hard. So the homework is that we have some term substitution like this. We know that we have the same rule as with types. So if you remember, we have this rule for types, like a kind of substitution rule for, okay, let's just name them. So one is called this ID rule, and the other called this composite substitution rule, rules for types. And the homework is to derive the same thing for terms as well. So we have this equation, and we also have this equation. And I claim that these two equations are just derivable from all of the previous stuff. Okay, from not all previous equations, we only need to use some previous equations to derive this. Okay. So what kind of examples should we have? Maybe we can look at some basic examples of substitutions, and like for example, what is the substitution, which is just flipping variables? Exchanging variables. It's a better. And so I want to get a substitution, and now I have to use some arbitrary type. So we don't yet have any types, but let's just assume that we have bool. And I want to define a substitution which goes from bool to bool, which like swaps variables. We already have a substitution which goes from bool to bool. It's called the identity substitution. So we already have something which has this type, but it's not what we want, because the identity substitution does nothing, but we don't want doing nothing. we want a substitution which actually does something. And informally, it would be so if I'm using names, then we have an X bool and we have a Y bool, and again we have an X bool and a Y bool, and the substitution itself can be defined as mapping. So we want to map the X variable, so the X variable lives in the target, and we want to map it to the Y variable, and we want to map the Y variable to the X variable. So this is kind of a swapping substitution. Okay, how can we define sigma formally? So it is very easy to define sigma using all of these names and these assignments of variables, but how can we define it formally? So how can we start? So we know that this is a substitution which goes into an extended context. So because
it will have to be something, comma something, comma something.
But
right?
why the extended context if we have the same variables?
So this is a substitution which goes into a context which has length 2, right? And this is, if you look at this informal notation, it's also a list of variables with length 2, right?
Yes.
So here we have to write
Formally.
formally.
It has to be epsilon, comma something, comma something.
Yes. Yes. So this is the formal notation for this list, right? Which has two elements. Now we have to write something here.
So I guess the first hole we can fill with Q because that's the innermost variable in the original context.
Yes.
And then the other one would need to be Q of P, like Q composed with P, maybe.
I mean, if you are using just de Bruijn indices, it's not that hard, because then we can write here 0,
sure.
and then we can write here 1, right?
Sure.
So informally, we can also have an informal notation for like mapping de Bruijn indices, and then this would say that, but now there is some flipping here, because this says that the index 1 is mapped to 0 and the index 0 is mapped to 1. So this notation is maybe there can be some confusion, because if we are using this de Bruijn index mapping notation, then on the left-hand side we have this decreasing indices. So if we are doing like this, then we have to start from 2 and we map.
So that's the answer. Epsilon 0, 1.
Yes, the answer is epsilon 0, 1.
But so is that epsilon Q and Q composed with P?
Yeah, so if we unfold the definition, then it's Q, and not composed, but substituted with P.
Right.
So when we, let's say when we evaluate this more or less, then it just basically we work from the right. So the leftmost variable in the context is given the value of the rightmost index in the substitution. So that's why it will be swapped.
Yes, yes. Yes, and we can also look at some example. So if we have any term which lives in the bool context, then we can apply the substitution, like the swapping substitution to it, and we can see what happens if we perform this substitution. So for example, let's have a term in bool with type bool. Let's define t to be, q. So the same as the 0 de Broglie index. And so I'm skipping some details about bool, but so there is a rule for bool which should be there, which just says that because bool is just a closed expression, it doesn't have any variables, so substitution on bool does nothing. And that's why this is well typed, because normally Q would have some AP type. So if we go back to Q, so Q returns in AP. But now I say that this Q just has type bool, and actually this is correct because Q has type bool P, but this type just evaluates to this type. Okay. So I say that the term is just the 0 de Broglie index, and now I want to evaluate t with substituted with sigma. So let's unfold the definitions. So I start with t sigma, and I know that t is q. So I have q sigma, but I know that sigma is this. So I have q this. But I also know, so the another thing which you should remember is that this comma, so this is a Snook operation, so it's parenthesized like this, right? Let's just try this out as well. So if I put the parents here, then I get this, and now I have a rule for q, right? So there is a substitution rule for q, which just projects out the last component in the substitution. So I get qp, and qp is the 1 de Broglie index. So the swapping substitution from the 0 de Broglie index computes the 1 de Broglie index. And likewise, if we are starting from the 1 de Broglie index, then obviously it will compute to the 0 de Broglie index. So let's also look at that one. So 1 is qp sigma. So this is the definition of 1. It's qp. Then we are substituting with sigma. And now we inline the definition of sigma. Okay, and what can we use now? And now we have to use the homework equation. So there is a homework equation which says that repeated term substitution is just substitution with composed substitution. So I mentioned as a homework, So we can rewrite this as follows. And now we can use the computation rule for p-composition, which just takes the initial part of a substitution. So this becomes epsilon extended with q. And now we can use the computation rule for q substitution. We just project out q. So this becomes q, which is 0. Okay, so maybe this is a bit magical, but I think it's still useful to think about this lookup intuition. So what is the kind of the lookup intuition for indices? So the lookup intuition is that if I have an I and I use some substitution on this I, then this computes to, so basically this is just looking up the ith element of sigma, counting from the right. Okay, so that's what is happening here. So if we go back to the definition of the swapping substitution, so this is a list which has 0 in this place and 1 in this place. But when we just perform the substitution, so no matter what index we put here, if we just perform a lookup operation. So if we look up the 0th element of this list, then we get 1. And if we look up the first element, counting from the right, then we get 0. So that's why it's the swapping substitution. Any questions about this example? Okay, then maybe we can do another very simple example, and this is called. Let's also put some space by here. Okay, so we have the diagonal substitution, the so-called diagonal substitution. And this is also, I mean, it's quite important because when we are doing meta theory, then it comes up in many places. And I can also explain why it's called diagonal, but it's very, very simple. Let's call it dia. So it goes from, and maybe this is, okay, so this is a very specific case of a diagonal substitution because it goes from bool to bool. Okay. And do you have any idea? So how can I define this diagonal substitution? So how can I define a substitution which has this type?
Well, I mean, we know the format. It will have to be epsilon, comma, something, comma, something.
Yes.
And I guess the only thing we can meaningfully do would be to put Q into both of the holes, because what else could we possibly do?
Yeah. Yes. So that's the only thing which we can do, actually. Okay, not the only thing, because if bool has some terms, then we can also do something like true or false. That would also have this type. but what we want here is indeed just QQ. And informally, so let's just name the things. So if we have an X bool, and then here we have an X bool and a Y bool, then diag can be defined as mapping X to X and Y also to X. So the action of this substitution. So what is the action of diag? When we use diag on terms or types, what happens is that if we have some term or type which can possibly depend on two different variables, then we are just swapping two, possibly like two different variables become the same. So two different words become the same after substitution. So if I have a t, which is a term bool bool, but now maybe we don't have very spectacular examples, because now for good examples, I should write some term which depends on two variables. Okay, maybe I can write some if then else here. Maybe if true, then Q as QP. But here I'm just assume that that there is a term for more, like there is an operation for bool, which is the if then else. It's an operation for bool. Okay. And we also have to assume that, that there is a computation rule for substitution for an if then else expression. So if I have if t, then u as v, and I'm doing a sigma on it, then I want to compute by just performing the substitution in all of the subterms. So then this becomes if t sigma, then u sigma as v sigma. Now if I am doing a t of diagonal substitution, then first let's unfold this. So if true, then q as qp, and this is epsilon qq. Now I am pushing the substitution inside the if then else. So we have this true substitution, this q, and this qp substitution. And okay, we also need to assume that because true is a closed term, then the substitution does not live on it. So the true part just computes, and then here, so this is the zero de Bruijn index. So from this list, we are just doing a lookup for the rightmost component, which becomes q. And this is the van der Bruijn index. So now we are looking up from the right the first. So it's also just q. And here we can see that two different variables are mapped the same there. Okay, I don't think we have a lot of time remaining. So should I start maybe introducing some type formers like pi or sigma or whatever?
I think maybe this is the best time to finish.
Stop.
Yeah, without
Okay.
introducing new things. I mean,
Okay.
but I have to say that compared to the end of last week, I am sort of understanding. But so just one question. So Q and P are also functions that in a concrete application or a concrete example have a value, or are these predefined in the theory to be something?
So Q and P. So here, so everything which we specified here is just what a CWF is, and then we can give like particular models of CWF, and in a particular model of CWF we have to define P and Q. So in any model, I have to give a definition. So first I have to define what sub is. So if we go back, so sub goes from con to set. So I have to define first what con is. So I have to give a set for con, and then I have to give a family of sets indexed over that con, which I just gave. And then I have to define every operation, and in particular, I have to define an element of the sub in the model. So in any model, the P has this type. In any model, the Q has this type. And so P and Q, they are not necessarily functions. Because it depends on what the definition of sub is. Because if sub is defined as like a family of sets, which is always a function, then P is going to be a function. But if sub is defined as something else, then P is not going to be a function in a model. And the syntax is one particular model which we just assume to exist. So question, it would make sense to start next time with a concrete CWF. My original plan was to first explain all of these type formers and then look at a concrete model. But actually, we can already look at a concrete model, and the concrete model is not something that we define. So here we are just assuming that there is always a concrete model for type theory, and the concrete model is just the syntax of type theory. So we just assume that there is a freely generated way of making a model of CWF. So I just say that there is a set of contexts which are the syntactic contexts, and I say that every context is given by the free finitely many application of these two rules, right? I say that there is a set of contexts, and the contexts are inductively generated by empty and extension. And I also say that there is a family of sets of types. And the type is also just inductively generated by the finite application of every rule. And likewise for sub, and likewise for TM. And that is just what we mean by the syntax of type theory. Does that make sense? Yeah, so we always have this kind of the freely generated model is the initial model, and maybe very shortly we can look at there is always a trivial model. The trivial model is basically let's make everything to be the singleton set. So con is defined to be this, and type of anything is defined to be this, TM, gamma is defined to be this, sum of one model is defined to be this, and then every operation is constant function returning star, and every equation works trivially. Okay, so there is this the trivial model, and the trivial model is actually terminal model. So there is a unique morphism from any model to the trivial model. And I think now we can finish now.
Yeah, thank you, András. And next week, Raphael will continue. And see you all next week.
Okay, I stop the recording.